we will see in a bit about these Blocopolymers, how do they stabilize the interface, okay? Usually we can add a third. Ternary is a third, okay? It's a fancy word for a third polymeric component, which is a polymer that has good adhesion with both faces, okay? If we disperse it very well, we obtain a ternary polymer blend, essentially. So we obtain a ternary polymer blend. Which essentially, because of the good interface and the strong bonding between the faces, now has efficient stress transfer under mechanical stress, okay? We also use reactive compatibilization, which is a technique that can take place during mixing of the blends, okay? So usually we use an extruder, we melt our polymers, and we mix them within an extruder. So again, we add a ternary polymer, a third polymer, which is miscible with one phase and capable with reacting with the other. And again, we have a formation of a Graft Copolymer. And the reactive extrusion and reactive compatibilization are very similar, okay? These two are very similar. Sorry. Finally, as I told you, one of the most, let's say, precise or neatest methods of compatibilization is to add a Blocopolymer in which each of the blocks has the same or similar composition to that of the component polymers of the blend, okay? So we have a polymer phase, a polymer blend that consists from the purple and the green polymer, okay? So we have polymer 1 and polymer 2. And these are immiscible, okay? So they create regions that are completely, you can see that this is a two-phase polymer, a two-phase blend. So how do we make them more to operate more friendly towards each other is by adding a Blocopolymer. This Blocopolymer have to have faces that are similar composition to that of the component of polymers of the blend. So if we have this Blocopolymer where the block A is a friend with polymer 1, thermodynamically friend, I mean, so we have they are from the same family of materials, okay, so they keep the Gibbs free energy at a minimum. And so we have a polymer that is from the same family with polymer 1, or it is miscible with polymer 1. And we have the second phase of the Blocopolymer. Usually we write the Blocopolymers like that, A, N, B, M, okay, or something like that. And phase B is, let's say, miscible with polymer B or friendly with a polymer B. Then we induce compatibilization of the polymer blend because this system has its lower free energy when the Blocopolymer is concentrated at the interface, okay? So when this region of block A does not pass to phase 2, okay? So it stays on phase 1 while block B stays on phase 2, that leads to the lowest free energy, okay? So we have a separation of blocks at the interface. Okay? So what we need is the Blocopolymer to be concentrated in the interface between phases, okay? So this is a AB diblock copolymer. You can see the A block of the residues in this phase, A residues in this phase, B residues in this phase, and this places essentially covalent bonds here. we have the formation of covalent bonds. Okay. This concept, as I told you, it's used widely in incompatible blend systems and usually leads to good control of the morphology combined with an improvement in interfacial adhesion, improved interface, and hence good mechanical properties. Remember that mechanical properties are the properties that are most significantly affected by the properties of the interface. Of course, the majority of physicochemical properties are affected by the interface, but mechanical properties are the ones that are most strongly affected by interfacial adhesion and generally the properties of the interface. A very, very simple problem. So we have this table, okay? And we have these data that were obtained from glass, which show the glass transition temperatures of different blends, okay, of natural rubber, NR. So elastomer 1 is natural rubber with different elastomers. So have a look at the table and please let me know what do you observe in terms of the difference between the values of the DG for the 50-50 blends, and what is the conclusion that you can get in essentially most of the times in these ones, okay? So let's focus on those three where we know the mixing ratio. What happens with these three blends? Please text me on WeChat to let me know what do you understand that's happening in these blends. Anyone? What information can we get from this table regarding the blends of natural rubber, the 50-50 blends of natural rubber? Have only one answer from 200 people? Come on. 2 answers, come on. I need a couple more. You should be able to very quickly understand what's happening here. Anyway, okay. As you can realize, by evaluating the glass transitions, you can see that this blend has 2 glass transitions. This one, the same. What did we say about the blends that have 2 glass transitions? essentially these are immiscible or incompatible blends. So 1 and 2, 1. These are immiscible, incompatible blends. Okay. On the other hand, if we look upon the blend of natural rubber with butyl rubber, okay, we can see that we have one glass transition at minus 60 Celsius degrees. That tells us that blend number 3, natural rubber with butyl rubber, is a miscible blend. Okay, so we have 1 Tg, 2 Tg. And from that, again, I repeat, Tg of the blend, WA, W, let's make it 1, W, so W1 Tg1 plus W2. Okay, very simple. Now, let's move on and let's move towards copolymers, okay? Copolymers, as I explained to you, are highly, much more sophisticated and much more, let's say, precisely fabricated materials, polymers, which have more than one type of repeat units in the polymer chain. And the process where we fabricate copolymers is essentially the process of copolymerization, okay, where two monomer repeat units enter the backbone chain of the polymer. As I told you, polymers usually phase separate when they're mixed, okay, and that leads to the worst of both worlds, okay. So we don't get the best of the properties of each polymer. How do we do that? How do we get the best of essentially two polymers? Is to covalently link the polymers, and in this case, if they phase separate, okay, this takes place at the nanoscale. So we create copolymers by copolymerizing two monomers together, okay. We create a polymer chain, a main polymer chain, where we control where we have the repeat units, how many repeat units do we have, and we control the bonding, okay. So essentially, by creating copolymers, we have creation of covalent bonds to link monomers or polymers afterwards, okay. It's the same. And in this case, even if we have a two-phase system, okay, what happens is that they phase separate at the nanoscale, and also we already have covalent bonds between the two phases. So the bonding is still strong, and we create these nanoscale assemblies, okay? Which is something desirable. And I'll explain later why this is desirable, okay? So what is important to remember about copolymers is that when we have a two-phase copolymer, the two phases self-assemble in the nanoscale. So copolymers, they self-assemble. That is very, very important. As you can understand, the properties of copolymers depend on how do we sequence the units along the chain, and we will see now how many different types of copolymers do we usually have, okay? And how do we fabricate them? So let's go to the notepad. Okay, so usually we have 5 types of copolymers. I think I write 4 of them. Let me see, sorry. So here I have 4, but we also have star copolymers, which are very, very difficult to make. So yeah, let's go ahead and look upon different types of copolymers do we have. Okay, so first of all, the easiest type of copolymer are essentially statistical or random, okay? In this case, we have A and B monomers, which are randomly aligned across the chain, okay? And so on. Let's say A, B are the monomers. The second case is an alternating copolymer, okay? Which the process that we use in order to create alternating copolymers is a polymerization called step growth polymerization, okay? Maybe Gabriel will explain more about this type of polymerization. We focus on the physics here. So for alternating copolymers, we have this kind of alternating sequence. Oh, sorry, this is alternating. And to fabricate them, we use a step growth polymerization. Usually, these alternating copolymers are easier to make when a chain with an A group is more reactive towards the B monomer. Okay, let me write this down. They occur when a chain okay. A third case, which is the most common type of copolymers, are Blocopolymers. These are made by leaving or anionic polymerization. Have you actually ever discussed these types of polymerizations with Gabriel or someone else? I don't know. These are very interesting kind of polymerization processes. And of course, as I told you, they require precise chemistry because in order to create this kind of very finely grown structures, we need to control very accurately the polymerization condition. Let me know if you had any experience in the past with one of your teachers. So we usually have diblock copolymers. Where we have, let's say, a structure of A, B, B, B. Okay, so in this case, these are usually termed A block B, okay? Or we can even have a tri-block copolymer. Okay, so in this case, they're written like that. Okay, we also have Graft Copolymers. These are made by coupling reactions. So in this case, we have a main chain with A's, let's say, and B is grafted on side chain, let's say. Okay, or it can be in different regions. Okay, it can be in different lengths. And finally, we also have what they're called star or radial copolymers, which are highly complicated to make, but very interesting as well. Star or radial. Okay, so let's say we have B, 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 A, 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 A. And so on, okay? So these look like that. So these are the 5 main categories of copolymers. Yeah, okay. And let's have a look at the morphology now. As I told you, the morphology of copolymers is a very important characteristic of let's say, the reasoning behind the fabrication of the copolymer, because by controlling the morphology of copolymers, we create these nanoscopic patterns with a high degree of regularity, okay? So by controlling the morphology, we create these nanoscopic patterns with high degree okay? So essentially, we create these two-phase structures where the one phase is in the nanoscale, okay? And by creating such tiny assemblies, let's say, by copolymerization, is a very important process in highly advanced technologies such as the microprocessor technologies that I will explain in a bit. Here I write microphase separated structures, okay? And I'll explain why I do that. When people firstly fabricated copolymers, it was before the advent of nanotechnology, okay? And people did not believe that these essentially structures could be that small. So they were calling them microphase structure, but they're really in the nanoscale, okay? These have dimensions from 10 to, let's say, 100 nanometers, usually, okay? So let's go to the notes again. And let's have a look. Let's design a bit. What happens when we move from the content of a monomer towards low content towards high content? Okay, let's say we have a Blocopolymer. Let's say phase structure. So if we have, let's say, what color should I use? I use red for A monomer, and I use blue, sorry, use blue for B monomer. Okay, so if we start from a low A content and high B content, okay, what is the phase structure of the two of the copolymer? Polymer in this case? So in this case, we have a cubic structure My drawing skills are not great. You'll realize that very soon. Okay, so in this case, the A monomer is concentrated on the edges of this cube, okay? And also at the front side and the back side, okay? This structure is a cubic structure, is a body-centered cubic. Okay? So all the circles are A monomer, and the rest of the cube is essentially representing the B. Is the B monomer, okay? In order to create this structure, the volume fractions of the A monomer that we use are ranging between 0 and 21%, okay, volume. So the volume A, in order to create this structure, ranges from 0 to 21 volume percent. Okay? This is for the cubic structure. This is for a percentage of monomer ranging between 0 and 21%. So if we increase more the range of the amount of A polymer or monomer in there, so let's say if we have a volume fraction of A ranging between 21 and 33%, 22 actually, and 33%, in this case we have a hexagonal structure. In this case, the A monomers look like logs essentially, in the way we stack logs in order to put them in let's say, in a fireplace, okay? So we have 1, 2, so 1, 2, and then we have 3 in the middle, okay? So we have 2 cylinders at the bottom and top, and 3 cylinders in the middle. We have 1, 2, and 3. I don't know, let me try and make it a bit better, but oh, sorry. I'm not sure how I manage. Okay, so these are cylinders, A cylinders. If you have a look, this I told you that this is called hexagonal structure, okay? And these are called cylindrical microdomains. They're called microdomains, but as I told you, they're really in the nanoscale, okay? They're between 10 and 100 nanometers. Okay? So in this case, we have 2 cylinders at the top and 3 cylinders top, bottom. And of course, as you can realize, it's called hexagonal because if you have a look at how these are arranged, these form a hexagon, okay? You can see the hexagon here. Okay, So if we increase even more the volume of the A monomer, what do we get if we go from 34, let's say, to 37%? In this case, we get the most complex structure, the most complex to draw as well. And it's called a gyroidal structure. It's a very intriguing structure, which is has these characteristics that is called, it's bicontiguous. Okay, I'll explain a bit more. Let me try and draw it because this is, as I told you, a bit complex. Okay, so this structure looks like okay, it looks something like that. Even though here in the middle it's slightly bigger. Okay, and here we have sorry. Here we have holes. I told you this is a gyroidal structure. And this structure essentially is called bicontiguous. What does that mean? It means that if we have continuous repeating unit cells, we can get from anywhere in the A block to anywhere else in the A block without crossing through the big block. Okay, let me write it down so it's easier for you to understand it. Okay, so that means that if we have to anywhere else, okay, so we can move only within this A structure without getting into the B monomer. Okay, so that is if we have continuous, let's say, pieces of unit cells. Okay, in this case we can move only in the A without crossing through the B block. Okay, this takes place at very narrow volumes though. Okay, notice that it's only 3 to 4% volume percentages in order to achieve this gyroidal structure. Okay, I notice that we're overrunning a bit, so I'll finish with the final morphology and then we'll take a break. So the final morphology ranges from the volume of a block being in the range of, let's say, 38 to 50 volume percent. And in this case, we have a lamellar morphology. What is a lamellar morphology? We have alternating layers between A, B, and A, B, okay? So in this case, the structure looks like that. It's like a cake, essentially. I should be making this with red, sorry. And of course, depending on the amount of, as you can realize, depending on the amount of the A monomer or the amount of B monomer in different cases, okay, we can control the thickness of this lamellar structure, okay? So in this case, we have the lamellar morphology. So we have alternating layers of A and B, and essentially we control the thickness of these layers by tuning the monomer percentage. Okay. Of course, as you can understand, now we reached 50% of the A fraction, okay? So in this case, when we go over that, we inverse the situation, okay? So if we have, let's say, 60% of A, we move on to having more A in this case. If we have, let's say, 30%, 35% of B, we have a blue structure that looks like that, and a red structure that has the rest of the unit cell. Okay, so so from now on, we have the inverse. I think there's a good slide in the course slides. We will see them in a bit. Sorry for taking a bit longer. Take a 10-minute break now, and we will continue in 10 minutes discussing about these nanoscale morphologies that we can create into Blocopolymers. Okay, so see you in 10 minutes. Okay, so let's continue with copolymers. They're very interesting. Where's my Apple Pencil? And they're very interesting characteristics. As I told you, the most interesting and most important characteristic of copolymers is that they're able to phase separate in the nanoscale. They form these nanoscopic patterns. Okay, these patterns have a very high degree of regularity, and also we have a very strong bonding. So if we have a look, that's what we essentially described so far. We have, with increasing volume fraction of minority phase polymer, okay, we create these nanoscale structures at different volumes, okay? And when we reach the lamellar stage, if we look, let's say, very carefully, very, let's say, nanoscopically into what happens in the interface, okay, we have change from A block and change from B block, okay, that they are bonded in this junction point, which is essentially the interface. Okay, and what is the type of bonds that we have in this junction point? Okay, we already talked about that. What kind of bonds do we have in these junction points in copolymers? Does anyone remember? What type of bonds do we have in between two monomers in copolymers? Oh, that wasn't one of you. Yes, covalent. I've repeated it several times, so please remember that copolymers form covalent bonds between monomers, okay? And because covalent bonds are very, very strong, okay, we have exceptional performance from the copolymers. And also, as we will see, because of these covalent bonds, we have very, very small dimensions of these nanoscopic patterns, okay? This is, let's say, the transition from a cubic to lamellar structure for a copolymer, okay, with increasing fraction of the A monomer, okay? And as I told you, after 50% from this stage, volume of A is higher than 50%, we inverse the situation. So here we have an inversed situation where the B phase is now the minority, the blue phase is the minority, and we have, let's say, an inverse in this case of the colors, but in reality is the change in which monomer or which polymer essentially phase separates, okay, which polymer let's say creates those nanoscopic patterns, okay. These are these are some nanoscopic patterns that we can observe. Please do not pay attention to these amounts, okay, but essentially it's very nice to see by TEM. This is TEM, we will talk about it in a bit, TEM images, that we can really observe these this pattern in styrene butadiene block copolymers, for example. By variating the amount of styrene in there, we can create these tiny structures. This scale bar here has dimensions of 500 nanometers, okay? So you can realize how small these patterns are. So, as we said several times, it is the most interesting part of copolymers is that they're able to essentially phase separate, self-assemble in nanometer scale into ordered structures through the process of phase separation. Okay, and thermodynamically, we say that the driving force in order to create that is the enthalpy of demixing of the blocks. That leads to a tendency for the blocks to phase separate in a way that is a bit similar to polymer blends. However, the structures that are created are much more fine, much more small, and they have strong bondings, good interface between the two phases. Okay, so that are the main difference between polymer blends and copolymers. Okay, however, as we said a few times now, in Blocopolymers, we have this extra constraint that the constituent blocks, the two phases, okay, they are connected through covalent bonds, okay? And because these materials are connected through covalent bonds, okay, these prevent the macroscopic phase separation, okay? The covalent bonds in copolymers prevent phase separation, okay? Of course, that also means that the dimensions of the ordered structures are very small compared to blends, as I told you, and they are not much larger than the radius of gyration. Let me sketch what is the radius of gyration. Come on. Oh, what did I do? Here. Go here. Okay. So the radius of gyration, the definition of the radius of gyration is if we have, let's say, a polymer chain that is entangled, as they usually are, okay? And we have this distance here that we know already, and it's called the end-to-end distance, okay? We already talked about that. Is the distance between the two ends, okay? This is statistical. It doesn't really matter if they are very close or very far, but we use this matter end-to-end distance. And if we essentially consider this blob, this entanglement of polymer, okay, as a circle, of course I drew it like that now, so it's easier for me to show you. The radius of gyration is the root mean square distance of the collection of atoms from the common center of gravity. So the common center of gravity of this circle is the center of this, essentially. If we consider this a circle, this is the center of the circle, and the radius of gyration is this radius, okay? So Rg, that is the root mean squared common center of gravity. That is the center of this circle that we make in order to have an approximation, let's say statistical approximation for the chain. Common and essentially the radius of gyration is given by this simple equation, 1/6 of the end-to-end distance, okay? The square of the average end-to-end distance. So as you can realize, the radius of gyration is a very, very small number. So let's go back to our notes essentially. And as I write, two factors affect the phase separation. We have a minimization of the area of the interface between two microphases and maximization of the entropy of the polymer change. And what is the most important in this slide is how do we control the phase structure, okay? And we have three parameters that affect the phase structure. How do we control it? Firstly, as we discussed already, is the composition of the copolymer. By controlling the composition of the copolymer, we know that we induce a certain phase structure based on the percentages that we saw already. The degree of polymerization is also something that allows us to control how much we have one monomer growing within the main chain of the polymer, okay, that is X, okay, because both these two parameters look same, okay. This is pronounced X, and also we have the Flory-Huggins interaction parameter He, okay, that is Greek He. Okay, these are the three parameters that affect, that control essentially the phase structure. Okay. So, what happens in essentially if we have a Blocopolymer that is essentially transformed from an ordered state to a disordered state? As you can realize, when we have a diblocopolymer, what is it? A, B, 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 A. Okay, this is how monomers are arranged in a diblocopolymer. When we have a diblocopolymer, we have order transition. Okay, we have order. Sorry, not transition. We have order. So we have one phase here, the yellow phase, and with another color, let's say this one, we have the second phase, alpha and A and B phases. Okay, this is the ordered situation. If we transform this homogeneous diblocopolymer into heterogeneous microphases, this is a disorder transition. So we go from nanophases to micron phases. So essentially, this can represent a type of compatibilized okay, while here we have a pure copolymer. Okay, this order to disorder transition occurs at the critical value of the product He times X. Okay, it's characterized by the balance of enthalpic and entropic structures. It's not possible to evaluate that in the context of this course, but simply I'll tell you that for a symmetric diblocopolymer, we have that this critical value of He times X for a symmetric blocopolymer means that we have equal amount of A and B. Then this critical value, which we will see in a bit, that is called a weak segregation limit, is 10.5. For a symmetric polymer blend, okay, you can see that this value is only 2, okay? Why is that? Why is it much smaller? Because we have a much higher loss of entropy in copolymers compared to blends, okay? And the entropy is proportional to the degree of polymerization, okay? So we have For a symmetric polymer blend, in order, if you want to observe this and calculate this, you need to go to this equation that we discussed already. If you look at this equation, okay, and what did we say? We have a symmetric polymer blend. What does that a symmetric polymer blend mean? It means that we have x1 equals to x2 equals to 0.5, okay? So if we substitute here in this equation, we have that the critical value for this parameter can give he critical equals to 2, okay? And it's easy to see, it's interesting to see how much different these two products are for copolymers and polymer blends because of the loss of entropy in copolymers, okay? We still have a certain amount of entropy in copolymers, but the situation is much more ordered compared to blends. Now, let's have a look at the phase diagram for Blocopolymers. And essentially, we call this a phase diagram. It's not absolutely a phase diagram, because usually phase diagrams are essentially functions of temperature versus composition. In this case, we have a phase diagram of this product, He times X over composition, okay? Let's go back and draw it. Come on. What am I doing? Okay, so if we want to create this phase diagram for polymer blends, okay, we have the y-axis having the product of the Flory-Huggins interaction parameter times x, the degree of polymerization, over F to A, okay? That is the amount of monomer. So the phase morphology, the phase diagram for, so what did I write? So the phase diagram for a copolymer looks like that, okay? We have here we have a disordered phase. And within these limits, as we will see now, we have an ordered phase, okay? So we start from low amounts of A, and we produce this body-centered cubic phase, okay? This is the BCC phase. Then we said we pass on through the hexagonal phase. Then we have the most narrow phase, that is the gyroid state. Yeah, my drawing is terrible, but anyway, get it. The gyroidal phase. And finally, in the middle, we have the lamellar phase. Okay? Can someone tell me, if I have, let's say, a 50% amount of monomer, okay? And I increase the temperature. Can you tell me what will happen? How do I move? How do I affect the phase of the copolymer? What happens if I increase the temperature? Does anyone have any idea? Because we said that the phase diagram essentially is a function of temperature versus, let's say, an answer from Juan. Anyone else? What happens if I increase the temperature? One more answer. Okay. Indeed, we will move towards the disordered phase. Okay. And why is that? Because we already said that the Flory-Huggins interaction parameters equals with alpha plus B over T. Okay. A and B are constants that are positive. Okay. So he is proportional to 1 over the temperature. So in this diagram here, we have decreasing temperature. Okay? This value here is around 10.5, and it's called the weak segregation limit. Okay? So in this case, we may say that we pass from a disordered phase to an ordered phase. However, it's not, the phases are not absolutely or very greatly defined. They are in nanoscopic patterns, but they're not still perfectly defined. Okay? So this is called the weak. Okay? And in contrast, for you to understand, a strong segregation limit is around 100, okay? So strong okay? So at a strong segregation limit, we have very, very finely defined morphologies, nanoscopic morphologies, based on what we said. That are either cubic or lamellar or gyroidal, whatever it is, depending on the different parameters that we control. Okay, and what are these parameters that we control in order to set the structure of a copolymer? So we control the degree of polymer. Oh, no, we don't want that. So we control the degree of polymerization. We control the temperature. And 3, we control the weight fraction or the volume fraction. Okay? Now, go back to the slides. Yeah, we discussed about this. Forget about this slide. This is wrong. Nice. Sometimes it is a method to control the structure, let's say, of a Blocopolymer by introducing, as I said, a third polymer, a polymer that is compatible with one of the faces, or it's a homopolymer. I'll just use this example to make this a bit clearer. It's not that important. So we have a styrene butadiene Blocopolymer, and what do we do is add 20% of polystyrene. Okay, so by adding more weight of the polystyrene, essentially we create this structure. But again, this is not something perfect, so generally it is not preferred, because it is a kind of a combination between copolymerization and blending. Okay, so it creates not so ordered structures, and we lose the control that we have, and also it can create weak interfaces. Okay. These are some examples of some commercially available copolymers, and the most characteristic one is Radial by General Electric. It's a combination of polystyrene and polyphenol ether. Okay, and it is used in the majority of computer housings. Okay. It's not that important. Anyway, so how do we observe these very, very nicely morphologies? Okay, so the most direct method for the visualization of these phase domains in Blocopolymers is transmission electron microscopy. Okay, or TEM. You probably have heard already about transmission electron microscopy. I will not give you more information, but if you want, let me know. I can provide some information. Usually in this case, specimens are prepared by casting film from solution. And then we produce this equilibrium morphology, which is then ultra microtome to create ultra thin sections. In order to do this cryomicrotoming, we use cryogenic temperatures. Does anyone have any idea why we use cryogenic temperatures? Cryogenic temperatures are minus 100 Celsius degrees, let's say. Does anyone have any idea why do we use cryogenic temperatures? In order to create these very fine, these ultra thin sections, ultra thin samples? Why do we need to make these samples so cold? In order to cut them. I have one answer, which is quite close, actually. Anyway, don't have too much time before we finish. So yes, indeed, ZGA, if I'm, my pronunciation is terrible, apologies for that. So indeed, to limit vibration of atoms, essentially what does that mean? It means that we want to go as much far away from the glass transition temperature. We want to have the change completely frozen, okay? So by freezing the change completely, we avoid damage or we avoid any distortion of this nanoscale morphology during cutting, okay? So that's why we use these cryogenic temperatures. So you can see some very characteristic morphologies that we already discussed. So for lamellar morphologies or for, let's say, which can be, I don't know, around 45, let's say, volume percent. Or bicontinuous gyroidal morphology, which can be, I don't know, I think it's around 37 or so, 34 or something. Okay, so you can see how nicely we can observe these nanoscopic patterns. Okay, however, there is a problem with transmission electron microscopy. These are very small samples. If this is the region of this is a scale bar of 50 nanometers. This photo is 250 times 250 nanometers. Okay, so we have only small two-dimensional projections, small regions, and we need to have a look to understand if the majority of our samples shows these morphologies. Okay, and how do we do that? We do that by using another technique that is called a small angle X-ray scattering. Okay, the advantage of small angle X-ray scattering is that it provides information from the whole of the sample. And if we look at this example, it's called SAX. Okay, so if we look at this example where we have a polyisoprene copolymer with a lamellar microstructure, and we let's say test the sample through small angle X-ray scattering, we obtain this this plot where we have this scattering intensity, and here we have the scattering vector. The scattering vector is a function of the scattering angle. And this is the wavelength of radiation, which is going to be constant, okay? It's going to be set by the equipment. So if we combine this with Bragg's law, which is this very simple equation, okay, we obtain the lamellar plane spacing, which essentially gives us, if we have a lamellar structure like this one, it gives us the spacing between the two lamellas, okay? So this D is equal to the ratio of 2pn over the scattering vector, and n is the order of reflection. So as if we go to the graph, we can see that this one, the first peak, is from the first, let's say, lamellar plane. So we have one order of reflection, second, third, and the fourth. So these represent reflections by subsequent lamellas. Okay. And in this way, we can obtain parameters such as dimensions of our structures. Now, let's have a look at some characteristic types of materials of copolymers, which are used extensively as examples and as, let's say, commercially available products. And I'd say that one of the most common examples in textbooks about copolymers is the styrene butadiene. It's called rubber type of copolymer, okay, because it mostly shows rubber characteristic. So we combine, what we do in order to create this copolymer is we combine polybutadiene with polystyrene. Okay, let's have a look at the characteristics of polybutadiene and polystyrene. Polybutadiene is a very, very soft elastomer. So because it is a very soft elastomer, it shows resilience, which is low modulus, or flexibility, high flexibility. Good toughness. The toughness, as we said, is the area under the stress strain curve. Okay, so as you can realize, if we're able to extend our elastomer much more, we obtain good toughness. However, it has some negatives. It shows poor resistance to oil, solvents, and oxidation. That is because it has very low or zero crystallinity. Okay. So what we do in order to let's say combine the properties of polybutadiene and polystyrene, which is a thermoplastic. I don't know how this here. It is only a thermoplastic. Please delete the. I don't know why the thermoset is there. Polystyrene is a thermoplastic, okay, which is very common. It's easy to process. It is chemically inert because it has high crystallinity as a result of no, it's chemically inert because it has this side group, phenyl group here, the p-phenyl ring here. Okay, so it shows good resistance to different acids and oxidizing agents. However, mechanically it is very brittle. Okay, so because it is brittle, it shows high modulus and low elongation. Usually the modulus of polystyrene is around 3 gigapascals. Okay, so usually we create styrene butadiene random and block copolymers. The random copolymer shows a single phase, so properties intermediate to those of the parent homopolymer. And also we create graft copolymers, which essentially are the properties are controlled by the multi-phase character of the copolymer. And essentially, how do we control this multi-phase character with essentially the parameters that we set? So the degree of polymerization, the composition of our material, and also with using testing it at different temperatures. Okay. Let's stop here. We will finish this part tomorrow. It's only gonna take us 5-10 minutes, and then tomorrow we will start focusing on polymer processing. Okay, so it was good seeing you today. I don't see any questions in the forum, so I guess you either understand everything that I'm telling you or you understand nothing that I'm telling you. So it's either one or the other. So probably you didn't have any time to revise, but whatever questions you do have, don't hesitate to email me or text me or post in the forum. Okay. Good to see you. Enjoy your evening, and I'll see you tomorrow. Bye, guys.